All right. Well, here, I'm going to do this. I'm going to set my microphone down. That'll work better, I think. Okay. All right, before I get into the lesson, there's kind of a basic thing you probably should have learned back in algebra that I need to emphasize. This is very important. Without this, you're not going to be able to set up today's problems correctly. So here it is. All right, obviously this is the graph of the parabola y equals x squared, which, by the way, if you solve for x, that equation turns into x equals plus and minus square root of y. So those are the same equation. It's just they're solved for different variables. Okay? All right. Okay, part A here. The vertical distances then between the x-axis and the graph can be represented by taking the x value and squaring it. So for example, if I wanted a distance from that point to the x-axis, what I would have to do is take whatever x value is here and plug it into the function y equals x squared, and whatever x squared is gives you the distance, right? Straight up and down. Same thing here. If I wanted to find that distance between that point on the curve and the x-axis, again, I would simply have to take that x value, square it, and that would give me the distance. Got it? So in general, can't you just say the distance vertically between the graph and the x-axis just comes from x squared? Do you agree? All right, now watch this. What if I wanted the distance between any point on the parabola and the y-axis? How would I get those distances? Well, I would take the y values here, whatever they are, and plug them into this equation, right? So I would just take the square root of y, the square root of the y value, and that would give you the distance horizontally from the curve to the x or to the y-axis. Do you understand that basic concept from algebra? Okay, well, if you didn't before, you need to now. All right, then. What if I said, what's the distance between any point on the curve and the vertical line x equals -1? This is -1 here. Okay, write down what you think it is there in that blank. Write it down. What do you think it is? Give me an expression that represents the general distance between any point on the parabola and the vertical line x equals -1. What's that distance from left to right? What is it? All right, Jason, what is it?
It's -1 plus √1.
Okay, but be careful. Distance. 1 plus, yes. 1 plus the square root of y. You agree? Because it's the square root of y from here to the y-axis, and then it's another 1 unit in between, isn't it? Yes? Okay. All right, so start thinking like that, and now I'm going to get into the hard part of the lesson, the new stuff. And again, this is not easy. This is not easy. You got to really pay attention. This is going to take a while for me to develop today's formulas. Okay, so let's start at the very beginning. Let's review here how we derived the integral formula for the area under the curve. Let's go back to the very, very first day. This is what I did. Okay, if you wanted to find the area under the curve, in other words, between a curve and the x-axis, say from x equals a to x equals b, this is what we did. Okay, to find the area under the curve, the first time we talked about it, we approximated. So notice there's an approximation symbol there. I simply added up a bunch of rectangle areas, right? That's what a Riemann sum was, just a sum of the rectangle areas, and that gave us nothing more than an approximation for the area under the curve. Do you remember that? All right, now let's talk about some more specific things with that. Okay? When we took the c sub I values, or x of I think I called them at the time, and plugged them into the function, that gave me the y values, or the heights of those rectangles, didn't it? Yes? I think I called them x of I instead of c sub I, same thing, right? And then I plugged them into the function, whatever the function was, and those gave me the heights of the rectangles in my Riemann sum. Do you remember that? Okay, and then I multiplied them by the widths of each subintegral, which I called delta x, right? Are you with me? Got it? Okay. And then what did I do? Well, again, all that is right there is one rectangle length times width. And then I added a bunch of them up, right? In other words, I did a summation. That's just adding a bunch of length times width, right? And that, again, that gave me an approximation for the area under the curve. Thank you. And then at that point, I talked to you guys about this, and you all agreed with me that how could you go from these area approximations to the exact area under the curve? Well, we talked about the more and more rectangles you squeezed in there, the better the fit, right? And so to go from the approximate area under the curve to the exact area under the curve, we took the limit as a number of rectangles went to infinity of my previous step, okay? So this is one Riemann sum, okay? And if you take the limit of those Riemann sums as a number of rectangles went to infinity, we then had the exact area under the curve. Do you remember that? You remember that? Okay? And so then, after that, we went to integrals. And so what happened with the integration was this. The integral, if you think about it, what it does is the integral accumulates, okay, a bunch of things on an interval. And so what happens is this turned into f of x, the delta x turned into my dx in my integral, and then the integral accumulated all the Riemann sums as the number of rectangles went to infinity. So again, the limit of the summation turned into the integral, that f turned into that f, and then the delta x turned into dx. That's what dx is, right? A change in x? Yes? Got it? Okay? And so that's how we went from this to this. Okay? And again, if you don't remember that, it's all in the book if you want to look it up. It takes you through step by step and goes through a little bit more of the detail. But that's basically the highlights of what happened. Right? How we went from a limit of a bunch of Riemann sums to a definite integral, and these were equal by definition. Okay? All right. So now today we're going to do a similar thing. Okay? But instead of talking about area under the curve, okay, which will start out with a bunch of rectangle sums, this is what we're going to do. Okay? We're going to start out with a function, and we're going to start out with the area under the curve from A to B. But instead of finding the area of that thing, this is what we're going to do with it. We're going to pretend like we attach that shape right there to the x-axis. So imagine taping it like that. Okay, so okay. So again, you see that region right there? There it is, okay? Now imagine taping that to the x-axis. Okay, so this pencil's my x-axis. Suppose I tape it like this. Is that how, yeah. All right, and then what's going to happen is this, is I'm going to spin it like this. I'm going to rotate it around the x-axis, okay? So imagine doing that really fast, and then I'm going to form a three-dimensional solid doing this over and over and over. Do you see what I'm doing? Okay, and so what's that solid going to look like? Yeah, it can kind of look like an ice cream cone, isn't it? Yes? You understand what I'm doing here? Yeah? Okay, so that's what we're going to do. We're going to take a two-dimensional region like that, and we're going to rotate it around, in most cases, the x or the y-axis, and we spin and rotate that around. You can see a three-dimensional solid being formed. Okay, you can imagine doing this on a computer, and then get, you'll have a better idea of what the solid looks like. All right. Let's say something. Thought I saved it. Okay. Okay, so in this case, instead of taking that shape that I had, they're going to take that purple shape there, okay, and they're going to rotate it around the line y equals -1. Okay, and so watch what happens. See how they rotated that around the line y equals -1 and it formed that three-dimensional solid? Did you see that? Okay, so that's another example of what I'm talking about. Okay, how you can go from a flat region and spin it, and it forms a three-dimensional solid of some kind. Right? Does that make sense? Okay, now the only difference is that mine's not going to have a hole in it. Okay? All right, so mine's just going to be, because the region lies completely against the x-axis when you rotate it, there's not going to be a hole down the middle like there was on that one I just showed you. Does that make sense? All right, but I'll show you some of those later. Okay, but I wanted to start out with a real simple one. Okay, so I think you have an idea what I mean by forming a solid of rotation or revolution. Okay, now, so what we're going to do then today is we're going to find the volume of those types of solids that we get by rotating a two-dimensional region. Okay, so here's how it's going to go. Ready? We're going to start by taking a rectangle inside the region, just kind of like we did with Riemann sums, right? But instead of finding the area of those little rectangles, what I'm going to do is imagine spinning that rectangle along with spinning the whole region. So if I spin one of those rectangles, isn't it going to turn into that? Like a real thin disc, like a coin? Do you agree? That's what's going to happen when you take one of those rectangles inside the region and spin it. Okay, you're going to get like a thin disc or like a coin. Okay, now let's talk about one of those discs. What's the volume of a disc? Well, a disc is just a thin cylinder. And how do you find the volume of a cylinder from geometry? Isn't it just area of the circular base times the height or thickness? And so if I call r the radius from here to here, okay, I call that r, the distance from here to here, because obviously when I rotate it, it becomes the radius of my disc, right? So I call that distance r. Okay, obviously the distance here is delta x. Are you with me? And so after I spin that rectangle, I get that disc, which has a radius of big R, and it has a height or thickness of delta x. Would you agree with that? And so I end up with that, or just pi r squared delta x as the volume of one of those little coins or discs. Are you with me? All right? So where do you think this is going? Obviously, if I take a bunch of those discs and pile them next to each other, starting here and stopping here, and then I add up all those disc volumes, isn't that going to serve as an approximation for the volume of that solid? It's just going to be an approximation, isn't it? It's not going to fit exactly, so it's just going to be an approximation. Okay, so that's where I'm going next. So if I take the sum of the volumes of several of those thin discs, stacked next to each other, starting at A and ending at B, basically you're going to be adding up or summing a bunch of those pi r squared delta x's that I just described on the previous page. Okay, now, here's what's coming next. How can we fit more and more discs in there? How? By the way, before I go too far, let me show you something here. Yeah. For example, suppose when you took a region and rotated it, you got this type of a solid. Well, if you use 5 discs and add those volumes up, you're going to get an approximation that's not very good. If you use more discs, you see how the more discs you use, the better the fit? So again, adding those 5 disc volumes up is going to give me an approximation for the volume of this. Using more discs is going to give you a better approximation. Using more discs is going to get closer and closer to the actual volume of this three-dimensional, looks like a sphere kind of. Are you with me? So do you agree the more discs you use, the better the approximation? Yes? Okay. Now, so that's where I'm going next then. So then the next question is, well, how do we make more discs fit in there? Well, remember, when you saw those AP problems, and some of those AP problems with the tables, the widths didn't all have to be the same, did they, on the Riemann sum? And that's the same thing here. The delta x's do not have to be the same, okay? Okay, so if you got a bunch of disks with a bunch of different delta x's, for example, if you take the widest one, okay, that's what this stands for. I know you've never seen those double bars on the delta x, but that just means that stands for the widest one. Okay, so if you take the widest one and make it smaller and smaller by making it go to 0, isn't that going to create more and more room for more and more of those disks? So isn't that one way we can force the number of disks to increase? By making the largest delta x smaller and smaller? You getting this? Okay, I told you it's complicated. Okay, and so that would make the number of disks go to infinity, wouldn't it? By making the widest one smaller and smaller. Are you following me? Okay, hang in there, guys. I'm almost there. Okay, so this is how it all plays out then. Ready? There's the volume of one of the disks. That adds up a bunch of the disk volumes, right, to get an approximation of the volume of the solid. And then this, taking the limit of those as the widest one gets smaller, in other words, as that goes to 0, basically making that go to 0 is the same as making the number of disks go to infinity. And so just like before, what happens? The delta x becomes dx in my integral. That just turns into that, same thing. And then the pi that was there, I pull out front. Okay, there was a pi there. Pull it outside. And then the limit of the summation, by definition, turns into the definite integral again, just like it did back with areas under the curve. Are you following me? Okay, so here we are then. That's where we're at then. That will give you, and there it is again, by finding that integral, you will have the exact, this is not an approximation, this is the exact volume of the solid that I described earlier, right? You with me? Okay, now, and again, what is R? R is the what? The radius of any representative disk inside the solid. And it's very important that you see something here. What did I rotate it around a minute ago when I did that? What did I rotate it around? I rotated it around the x-axis, which is a horizontal line, isn't it? Isn't the x-axis a horizontal line? So if you ever rotate it around a horizontal axis of revolution, you're going to be taking pi times the antiderivative from an x to an x of the radius in terms of x squared dx. What happens if you rotate it around a vertical line, like the y-axis, for example? How are things going to change? Well, you're going to go from a y to a y. Your radius of any representative disk will be in terms of y, dy. Is that clear? Yes? Okay? All right, so here we go. We're ready to do some examples. Okay, so example 1. Again, just like last time, you're not going to get very far without a graph. So always start today's problems with a graph. That goes for the homework, that goes for the test. In fact, on the test, I'll give you the x and y axis to make sure you show your graph before you do anything else. Is that clear? Okay, so here we go. It says find the volume of the solid formed by revolving the region bounded by this graph, the x-axis, and the lines x equals 0 and x equals 2. Okay, I circled all those in green for a reason. Okay, so let's just go with those 4 things and let's draw the region they're talking about. Ready? What is this? What is that? That f of x equals x squared is a what? Parabola. Give me some points, quick. 0, comma, 0, 1, comma, 1, 2, comma, 4, and then by symmetry, I'm going to have those other points corresponding over here, right? Can I use a pencil, guys? Is that okay with you?
For your birthday.
Okay. Who? Max is not here today.
Okay,
Yeah. Okay, so again, we're just getting started, right? I'm going to draw that parabola with a pencil here so I can erase something later. Okay, there's the parabola, and then where's the x-axis? The x-axis is here, yes. And what else do you have? The line's what? X equals 0, which is there, and x equals 2, which is here. Okay, everybody see how I drew those 4 things there? Sid, heads up. See how I drew those 4 things? Those are my kind of like my constraints that form the region. All right, so where do you see the enclosed region between those 4 things? Where is it? Isn't it right in here? Isn't that the enclosed region that they're talking about between those 4 things? All right, so what I want you to do now is erase everything else. Okay. So I'm going to start with that region right here. And I'm going to rotate it around what? What's it say to rotate it around? The x-axis. And so what I like to do is I like to put a really dark dotted line on the axis of revolution so it's really clear what I'm rotating it around. Okay, so that's my axis of revolution. That's the line I'm going to rotate the region around. Okay, so again, imagine taking that region and spinning it around the x-axis. It's going to form a 3-dimensional solid. That's, I guess the best way to describe it is going to kind of look like a Hershey's Kiss, isn't it? Yes? Everybody knows what those look like? Okay? And so that's the solid, that Hershey's Kiss-shaped solid is what I want to find the volume of using calculus. Are you ready? Okay, so here it goes. What I want you to do is always the following. I want you to draw one of those representative rectangles inside the region perpendicular to your axis of revolution, always. Okay? And then imagine rotating that rectangle around the x-axis. Aren't you going to get one of those thin discs or coin type shapes? Yes? Okay, what's going to be the radius of that disc from there to there? What's going to be the radius r from here to here? What is it? Well, remember what I said at the beginning of the hour? Remember I said you have to start thinking like this to get the distances between a graph and the x-axis or between the graph and the y-axis. In this case, we want the distance between the graph and the x-axis. So what formula is going to represent the general distance from here to here? What is it? What is it? X squared. Everybody agree? So my radius in general of one of those discs is going to be x squared. Agreed? That's my r sub x, okay? And then I'm going to use this formula right here. Right? Why am I using that one in terms of x instead of this one? Why? Why? Because I'm rotating it around a horizontal line, the x-axis in this case. Is that clear? Okay, so here it goes. All right, so the volume can be found by taking pi times the antiderivative of what? My radius, r sub x, which is that squared, right? Isn't it? Don't you take your radius and square it, right? It's your r sub x formula squared, right? Yes? dx from what x to what x? Well, think about it. What x value does my region start at? You tell me. 0. And what x value here does it stop at? 2. And again, don't forget your pi. That's a common mistake. That students get so caught up in the integral, they forget to put the pi out front. Remember where the pi came from, right? That helps you remember to put it in? Yes? Okay. All right, so it's real simple then. Here we go. Let's finish this. Okay, so basically I'm going to be integrating x to the 4th dx, right? And so what's the antiderivative? X to the 5th over 5, right? And then to finish it, don't you plug in the 2? What's 2 to the 5th, guys? 32. And then subtract what I get when I plug in the 0? Yes? And so what do you get, guys? 32 pi over what? 5, which if you turned it into a decimal, what would that be? Okay. Whoops. Okay, so 20.106. What? Units what? Units cubed. This is a volume. Okay, so that's the volume of that Hershey's Kiss type solid that I described earlier, that gets formed by taking that two-dimensional region and rotating it around the x-axis. Got it? Okay? Can you handle one like that? Okay, it's going to get a little bit more complicated, but that's a simple example for now. Okay? All right, let's do another one. And this one's a little bit harder. They're going to get harder and harder as we go through the examples. Okay, so the next one. Find the volume of the solid formed by revolving the region bounded by this graph and this graph. Okay, I circle those in green because those go together. I'm not going to worry about the y equals 1 till later, because these are the only two things I got to worry about that are going to form my two-dimensional region. Are you ready? Okay. So again, just think of that as this. And you can think of that as y equals 1. Okay, so what is this? This is a what? Parabola what? Shifted 2 up and opening downward. Okay, so it's definitely going to have a vertex of 0, 2, and then it's going to open downward like that. But let's get some more points. Ready? 1 comma what? 1. 2 comma negative 2. And then by symmetry, you can have these other points, right? Oof, I shouldn't have done that, but oh well. I should have used a pencil. Okay, but anyway, there's my parabola, and then I've got the line what? I've also got the line what? Y equals 1. And so those two things form my two-dimensional region. So where's my two-dimensional region, guys? Between those curves. Isn't that right here? Isn't that the region right there? Yes? Good. So that's the two-dimensional region that we want to rotate. Now, what are we going to rotate it around? This time we're not going to rotate it around the x-axis. This time it says to rotate it around what? The line what? Y equals 1, which is this. Isn't this right here my axis of revolution? Right here, the line y equals 1? Yes? Okay, and so if you take that two-dimensional region and rotate it around the line y equals 1, it's going to form a three-dimensional solid that's going to kind of look like a football, isn't it? Yes? Agreed? Does it look kind of like a football? Yes? Just to give you a visual of what the solid might look like after you rotate it? Okay. All right, so now be careful here. If it helps, I'm going to blow it up a little bit for you to see. Okay, so we're taking the solid that looks like this. I'm sorry, we're taking a two-dimensional region, I should say, that looks like this. And again, we're rotating it around this line right here. All right, so listen closely. Again, here's my region. Ready? All right, so the first thing I want you to do is always what? Draw a representative rectangle where? What did I say? Inside the region, perpendicular to your axis of revolution. So the rectangle better look like this. Trust me, if you don't draw that rectangle, you're not going to see what you need to do next. Draw that rectangle. How are you going to draw it? Inside the region, perpendicular to the axis of revolution, always. Is that clear? All right, now, if it helps, you can imagine rotating this. Again, you're going to tape it right here. There's your tape right there. And then you're going to spin that rectangle around that green line. It's going to end up looking like this, right? It's going to end up looking like that, like a thin disc or a coin. Do you agree? Yes? Okay? And again, what's the radius of that disc? Big R. Well, the radius of that disc is going to extend from here to here. Do you agree? All right, now we need to come up with a formula. That's the tricky part. What's the formula for that distance from there to there? Well, let me ask you this. What's the distance from that point down to the x-axis? Okay. Yeah, it's just the formula of the parabola. What was the parabola equation? Yeah, it was 2 minus x squared. Okay, that's the distance from here to here. But that's not what we want. We want the distance from here to here. So what is it? It's that distance, what? Minus this gap in here, which is 1 unit. See what I did there? Again, the 2 minus x squared gives you the distance from here to here. I don't want that. I don't want that whole distance. I want just the distance from here to here. So you're going to have to take that whole distance and subtract this gap, which is always 1. Is that clear? And that's going to give me a formula. And by the way, I can simplify that to what? 1 minus x squared. Okay, so that's going to give me the radius in general from here to here, one of those disks. Are you with me? That's the hard part. The rest is just plugging it into the formula and doing the integral. We're done with the hard part of the problem. You understand? Okay, so let's finish it now. Okay, so as I just said a minute ago, it's 2 minus x squared minus 1, which simplifies down to 1 minus x squared. Okay, so let's finish it. So, to find the volume of the solid that I described as kind of like a football, you would take pi times the antiderivative of what? Big R squared, right? dx from an x to an x. Okay, so be careful. Where does that region start? Well, it starts at this x value and it stops at that x value. Would you agree? Now, I don't want you to guess what those x values are. How am I going to get those x values without guessing? Yeah, aren't I going to have to set these two equations equal to each other and solve for x? Yes? Okay. So to find out where those graphs cross, I'm just going to set them equal to each other, and then I'm going to move everything to the right side. And then I'm going to factor. And I'm going to get what? X equals negative 1 and x equals what? 1. So clearly this is the point negative 1 comma something. This is the point 1 comma something. And really all I need is the x values, right? So I'm going to integrate from an x of negative 1 to an x of positive 1. Does everybody agree there? Yes or no? Yes? Okay. And by the way, just to go a couple more steps, this is what you would do next. A U substitution is not going to work there, so don't even try it. What you're going to have to do is you're going to have to FOIL that. So if you write it twice in FOIL, what do you get? 1 minus what? 2x squared plus what? X to the 4th. And then you're going to have to integrate, giving you x minus 2x cubed over 3 plus x to the 5th over 5. And by the way, I just integrated, so get rid of that. And then what? And then plug in the 1 and subtract what you get when you plug in the negative 1, and then multiply by pi at the end, and you'll get your volume. I don't have time to finish it, or the room, so I'll just stop there. But you understand how to finish it now? It's pretty easy to go a couple more steps and get the volume. Okay? All right. By the way, what is this method called? It has a name. You should really know it by name. What is it? It's called the what? The disk method, for obvious reasons. Because you're basically starting with a sum of a bunch of disks and then going from there. Is that clear? Okay, now the only time it works is when? Read this. This is a very important note. Sorry it's kind of just crammed in there at the bottom of the page, but it is very important. What does it say? The disk method only works when? When the entire region you're rotating lies completely against the axis of revolution. Is that clear? If it does not, then you're going to need to modify your formula. Okay, and that's where I'm going next. Do you understand, though, what I'm talking about? That the disk method is only going to work if the entire region, which it did in example 1 and 2, lied completely against the line you were rotating it around. There was no gap in there. Do you agree? Yes? All right, well, that's going to change on the next page. So let's look at what happens next. All right, so suppose the region you want to rotate ends up looking like this. Here's my red pen. Okay? Suppose that's the region that you get, and then you got to rotate it, for example, around this line right here. When you rotate that, region, what's going to happen is it's going to end up looking like this, isn't it? It's going to be a three-dimensional, I don't even know how to describe it. It's going to be, I mean you can kind of see what the outside is going to look like, but then when you look on the inside, when you look in here, this is all going to be hollow, right? That's all going to be cut out. There's going to be a gap in there. Do you understand? Okay? All right, and so you want to find the volume. In other words, how many cubic units of material would you need to manufacture that or to make it, okay? And so what you want to do is start with a representative rectangle. Where again? Where again? Inside the region, perpendicular to your axis of revolution. So that's what I did. Notice I just drew it inside the region, perpendicular to your axis of revolution. And then you can imagine rotating that around this line here. What's going to happen is this end's going to swing around like that. This end's going to swing around like that. And it's going to form like a donut, isn't it? Or a washer, okay? So where I'm going next is the washer method, or you can think of it as the donut method if that makes more sense. But you see how it, instead of getting a solid disc, you're going to end up with a hole cut through the middle of it based on the fact that there's some space in between here and the axis of revolution. Do you see how that hole gets formed? Are you with me? Okay, and now, so what's going to happen is, basically, this would give you the volume if there was no hole. And then so you're going to subtract the volume of the contents that would be formed by the hole. Okay? So that means you're going to take pi times the antiderivative of big R squared dx minus pi times the antiderivative of little r squared dx. Okay, so you're going to take the outside volume and subtract this inside here that I described as being hollow. Okay, so this is going to give you the hollow space that's going to be cut out of the whole outside solid. Do you understand? Okay, and by the way, is there anything stopping me from combining those into one integral? Is there anything stopping me from doing that? Can I do that? Sure. And so that's going to combine into that. And so there you go. So this is called the what? This is called the what? The washer method. So again, if you're in a situation where you're rotating some region like this, for example, around a horizontal line, you're going to take pi times the antiderivative from an x to an x of your big R squared, which is your outside radius squared, minus your inside radius squared. Got it? Okay, dx. And if you're rotating it around a vertical line, you're going to just change everything in terms of y dy from a y to a y. Got it? All right, now think about it. Read this. Everybody read this. The disk method that I did a minute ago is just simply the same as the washer method, except that little r turns out to be what? 0. And so if you take little r out of these formulas, don't you just get back to the disk method? Yes? Are you following me? Okay. So what I'm saying is this. You never really need to use the disk method. Just use the washer method every time. And if there's no gap, then you just make little r 0. Does that make sense? Yes? Okay? All right. Let's do some more examples now. Here it goes. All right. Example 3. It says, set up but do not evaluate an integral that can be used to find the volume of the solid formed by revolving the region bounded by these two graphs. Okay, so stop there. Okay, graph those two things. And again, I'm going to use pencil. So what does y equals square root of x look like? Well, we should know what it looks like, but give me some points. 0, comma, 0, 1, comma, 1. How about 4, comma, what? Yeah, 4, comma, 2. Okay? And so on. So it looks like this, doesn't it? Isn't that what the graph of y equals square root of x looks like? Okay? And then what does this look like? It's a parabola. Give me some points, quick. 0, comma, 0, 1, comma, 1, and so on. And then it looks like this, doesn't it? Agree? Yes? Okay, so where's the enclosed region between those two graphs? Well, that would be right here. Keep losing my red pen. So that right there is the region we want to rotate. Everybody agree with that? Yes? So at this point, if you want, you can erase everything else so it doesn't get in the way. Okay, and just focus on the region that you want to rotate. Okay. Okay, and so if you rotate that, what are we rotating it around? We're rotating it around the line what? Well, the x-axis. So everybody agree that this green dotted line is my axis of revolution? Yes or no? Everybody agree with that? Okay, so if you rotate that region around that green line, this is going to kind of swing around like this, isn't it? And you're going to end up with something like that. Okay, so kind of, I guess, and again, what's going to happen is this is going to be solid. This is all going to be solid, and this is going to be hollow. Isn't this all going to be hollow in here? I mean, you're going to have that as kind of like the outside, but this is all going to be hollow, isn't it, in here? Yes? So it's kind of like a gumdrop with a bunch of area in here cut out, a bunch of space cut out. Does that make sense? Good? All right, so we want to find the volume of that thing. And so what are we going to do to find the volume? Well, always start by drawing a representative rectangle where again? Inside the region and perpendicular to the axis of revolution. So there it is. Did I draw a representative rectangle inside the region that we're rotating and perpendicular to the axis of revolution? Yes, I did, didn't I? Okay, now imagine rotating that rectangle around the x-axis. What's going to happen is this is going to swing around like this. This point right here is going to swing around like this. This point is going to swing around like this, and you're going to get a like a donut, aren't you? Yes? Agreed? Okay. And what's the outside radius of that donut? Well, in other words, what's big R? The outside radius, big R, do you agree, goes from here all the way to the x-axis? Yes or no? All right, what is that distance in general from the x-axis to that top curve? What is it? Yeah, it's just square root of x, isn't it? Okay, now what's the radius of the whole of the donut? Well, little r, the little radius would go from here to here, wouldn't it? Isn't that your little r? From that curve to the x-axis in general, and what's that distance? What's your little r? What is it? X squared. Isn't it just the parabola function values? Isn't it? Yes? Okay, and so here we go then. So again, you can put those here. All right, and again, notice how they're in terms of x, because you're rotating it around a horizontal line. When you're rotating it around a horizontal line, you're going from an x to an x. Everything's in terms of x dx. Got it? Okay, so here it goes. How do I find the value of them, guys? Don't forget the pi. Anytime there's a revolution, there's a pi, right? Pi times the antiderivative of big R squared minus what? Little r squared dx from what x to what x? Well, that red region starts here at an x value of what? 0, and it ends here at an x value where the graphs intersect. You can see where they intersect. What is it? 1. And even if you didn't, couldn't you just set square root of x equal to x squared and solve for x, and you get x equals 0 and 1, wouldn't you? Wouldn't you? If you set those functions equal to each other and solve for x, wouldn't you get x equals 0 and x equals 1, which are my limits, which is where they cross, which is where the region starts and stops in this case? Yes? Okay? All right, so one more step, and we'll go on to the next example. Okay, so don't those cancel out? And don't I get x to the 4th here? And guys, please don't forget to integrate. And so you get what? X squared over 2 minus x to the 5th over 5. And then you'd plug in the 1 and subtract what you get when you plug in the 0, and then multiply by pi, and you would get the volume. Is that clear? Okay, I know I'm going kind of fast, but I think once I set it up, it's pretty repetitive, isn't it? Okay? So setting it up is the hard part. Any questions? Again, I'm flying and you guys aren't saying anything. Is this okay or not? You sure? Okay. Another one. This one's going to be real tricky. Okay, so here we go. All kinds of different things are going to happen in this one, so please listen closely. All right, this time, what's going to form my region? What's going to form my flat region? These. Those four things right there are going to form my flat region. So I want you to graph all four of those things. Are you ready? Okay, what's y equals x squared plus 1 look like? Quick. Parabola shifted up 1, opening up. Yes? So it's going to go through 0, 1, and then what's another point? 1 comma what? 2, and so on, right? All right. So there's my parabola. All right? And then I've got, you guys, the mistake you're going to make, and it's going to be a huge mistake, is you're going to confuse vertical lines with horizontal lines. Please don't do that. What does a line y equals 0 look like? It's the x-axis. Isn't this the line y equals 0 right here? What's the line x equals 0 look like? That's the y-axis. And then what's the line x equals 1 look like? It's a vertical line right here, isn't it? Isn't that vertical line? So does everybody see the region right here, that the enclosed region formed by those four constraints? Looks like this. Yes? With me? Okay. Now what I'm going to do is I'm going to erase everything else so it doesn't get too messy. Okay, so erase everything else and just focus on that red region right there that we're now going to rotate. And what are we going to rotate it around? We're going to rotate it around what? The y-axis. Doesn't it say to rotate it around the y-axis? So here we go. I'm going to put a dotted line there. Okay, and so again, what did I say you do next? You draw the represented rectangle where again? Inside the region, perpendicular to the axis of revolution. So watch. Have I done that there? Have I drawn a representative rectangle inside the region and perpendicular to the axis of revolution? Yes, I did. You see how I drew it horizontal this time? The problem is this. If I draw it there versus down here, I might get a different radius when I rotate. Do you agree? Yes? Okay, so in this case, you're going to have different r's depending on where you are, okay? All right, so first of all, what's it going to look like when I rotate that red region around the y-axis? What's going to happen is this is going to swing around like that. This is going to swing around like this. And what's going to happen is basically you're going to get a cylinder, right, with kind of like a little bowl-shaped space cut out of the top like that, and that's going to be hollow in there. Yes? Got it? And this is all going to be solid down here, isn't it? Yes? So you're going to kind of have like a, again, like I said, like a cylinder, and in the top there's going to be a little hollow bowl-shaped space cut out. Yes? With me, Sid? You don't want a bowl-shaped region cut out of your cooperation grade, do you? All right. Stay with me. Okay. Okay, so this is one of those cases where you're actually going to need to set up two separate situations. The first one's going to start here at y equals 0 and stop here at y equals 1, right here. Okay, so from there to there. So you imagine rotating this rectangle around. There's not going to be a hole, is there? You can read there's going to be no hole down there when you rotate this rectangle around the y-axis, no hole. So your little r is going to be what? 0. What's your big R? Well, your big R is going to go from here to here. What is the distance from there to there? Always 1. So your big R is going to be 1. Your little r there is going to be 0. Does that make sense? All right, now let's look from here to here. In other words, from y equals 1 to y equals 2 up here. If you rotate this rectangle around the y-axis, this is going to swing around like this. This is going to swing around like this. And you're definitely going to have a donut, aren't you? Yes? Okay, what's the outside radius of that donut? In other words, from there to there. What's your big R? 1. And what's your little r? What's the radius of the hole? Well, be careful. What is it? It's this parabola function value, but in terms of what? Y. And so if you have y equals x squared plus 1, aren't you going to have to solve that for x to get it in terms of y? So I'm going to subtract 1, and then what? Take the what? Square root. And so do you agree that that's the distance of your hole, the distance of the hole? Of your little r, in other words? Tricky, isn't it? Okay, so how's this going to set up then? Well, for this, you're going to take pi times the antiderivative from a y of 0 to a y of 1, and then big R in terms of y squared minus your little r in terms of y squared dy. Are you with me? And then you're going to add what? Pi times the antiderivative from what? Y equals 1 to y equals 2. Big R in terms of y squared minus little r in terms of y squared dy. And then you're going to simplify that mess and go from there. So you're going to have to do two separate integrals. Does everybody see why I need two separate integrals? The reason I need two separate integrals is because you get a different little r depending on where you are in the region. Does that make sense? Okay? By the way, that problem's off an old AP exam. Same exact question. They wanted you to set it up, but don't finish it. Because it takes long enough to set up. And anyway, so sometimes they do that on the free response to save time. They just have you set it up and stop instead of integrating. Is that clear? All right. All right. Last page or no? Okay. All right, again, this time I'm just going to have you set it up. I'm not going to have you finish it. All right, but in every one of these, A, B, C, D, and E, you're going to start with the same region. Okay, and what's the region going to be formed by? The region is going to be formed by what? The graphs of what? Y equals x squared. So again, it's just a parabola going through 0, 0, 1, 1, 2, comma what? 4, and so on. Okay? And by symmetry, anyway, it's gonna go over here too. Okay? All right. By the way, let me add something to that. Well, wait, I'll do that in a minute. What else do we have besides that? We have what? The line what? Y equals 4. And again, you're going to make a major mistake on the test by mixing up that with the line x equals 4. Please don't let that happen. What does a line y equals 4 look like? What type of line is it? Horizontal. So the line y equals 4 is up here, isn't it? Okay. And then where's the line x equals 0? The line x equals 0 is the what? It's a vertical line. It's the what? It's the y-axis, isn't it? All right, so now wait a minute. Don't you actually have two enclosed regions between those three graphs? So I'm going to add in here in quadrant 1. So you got to put that in there or you're going to be confused when you look at it later. So in quadrant 1 only. So where is the enclosed region between those three graphs in quadrant 1? Well, we'd be talking about only that right there, wouldn't we? So if you want now, you can erase everything else. Okay? All right. So we're going to be starting out with a region that looks like this. Everybody agree? Yes? Whoops. By the way, I'm going to draw that on all of them. Goes 2 here and then okay, so in every one of these, we're going to start out with the same region. But then what we rotated around is going to change from A to B to C to D to E. Are you with me? But in each case, you're starting with that same region. Are you ready? Here it goes. It's going to be fun. Okay, in part A, what are we rotating it around? The x-axis, which is here, right? So there's the axis of revolution right there. Okay, so what are you going to do next after that? Draw your representative rectangle where? Inside the region, perpendicular to the axis of revolution. Okay, so it's going to look something like that, right? Didn't I draw the representative rectangle inside the region, perpendicular to the axis of revolution? Now imagine rotating that rectangle around the x-axis. What's going to happen is this end's going to swing around like that. This end's going to swing around like that, and again, you're going to have a donut, aren't you? Yes, instead of a disc? Okay, so what's the outside radius? Now be careful. Look at that donut and realize that the outside radius goes all the way from here to here, doesn't it? Isn't that your big R? Agreed? What is it? 4. Agreed? Yes? Okay, and then your little r is the radius of the hole. So what's your little r? In other words, what's the distance from here to here in general? From the curve to the x-axis, what is it? X squared. Everybody agree with me? Yes? Okay, now, so then set it up. It's going to be pi times the antiderivative of your big R squared minus your little r squared dx from what x to what x? What's this point right here? That'll help. What's that point? Where do they cross? If you set x squared equal to 4 and solve for x, what do you get? 2 and negative 2, so clearly this is what? 2 comma something. By the way, you can see the y value. What is it? 4. So anyway, imagine a bunch of those discs, or I'm sorry, donuts, stacked next to each other. Okay? Imagine a bunch of them stacked next to each other. Where are they going to start? They're going to start here at an x value of what? 0, and they're going to stop here at an x value of what? 2. Okay, so I'm going to go one more step, and then I'm going to stop. Okay, so after simplifying, you get that, and then you would need to integrate, plug in the 2, and subtract what you get when you plug in the 0, and then multiply by pi, and you got your volume. Is that clear? Yes? And by the way, I didn't really describe what the solid looks like. I mean, you really don't need to do that as long as you're able to rotate the rectangle. I don't really care if you try and draw the three-dimensional solid, but if you're interested in seeing what it would look like, basically, again, this would swing around like this. Basically, it would be kind of like a dog food bowl, but when your dog's drinking out of it, when his tongue hits the bottom will go to a point, won't it? The bottom of his bowl would go to a point. Yes? Yes? You understand kind of what it would look like? Yes? All right, that's the best I can describe it. I don't know how else to describe it. Okay, good. All right, but the bottom line is if you draw the rectangle and rotate it and see your big R and little r, that's all you ever need to do on these. Okay? Got it? All right, next one. This time we're going to take the same region, but now we're going to rotate it around the what? The y-axis. So here's your axis of revolution. And what did I say you do next? You draw your representative rectangle where? Inside the region, perpendicular to your axis of revolution. Stay with me, guys. So it would look something like this, wouldn't it, in general? Yes? Okay, now imagine rotating that rectangle around the y-axis. So this end would swing around like this. And since the inside of the rectangle always touches the y-axis, do you agree there's going to be no hole? No hole here? Agreed? No hole? Okay, and so little r is 0 because there's no hole. And big R would go from the y-axis all the way to here in general, which would be what? What's the distance from here to here in general? Well, wouldn't it just be the function values in terms of y? And so what was my function? Y equals x squared. And so if you solve for x, what do you get? If you take the square root of both sides, you get x equals what? Square root of y. Do you agree that square root of y would be the general distance from here to the y-axis? Would you agree with that? That would be your big R? Yes? Okay? All right, so how would it set up then? You'd need your pi times the antiderivative of your big R squared in terms of y minus your little r squared in terms of y, dy from what y to what y? From a y of 0 here to a y of what up here? 4. And if you want, you can go one more step and simplify that mess, and you would get this. And then from there, don't forget to integrate and get y squared over 2, and then put in the 4. Subtract what you get when you put in the 0. You could tell me what it is. You could do that in your head. What is it? You get y squared over 2 and plug in the 4. That gives you what? 16 over 2, which is 8 pi. Isn't it 8 pi? Which is 20-something cubic units. Yes? Good? Yes? Okay, question? Because again, you agreed that the graphs cross at the point 2 comma 4. And remember, when you're rotating it around a vertical line, everything's in terms of y dy from a y to a y. So if you stack those disks on top of each other, aren't they going to start here at y equals 0, and aren't they going to stop up there at a y value of 4 if you stack a bunch of them on top of each other throughout the region? Yes? Good? Okay. All right, next one. This time we're rotating it around what? The line what? Y equals 4. Now this is tricky, really tricky. Okay, this is the one where students have the most trouble. So everybody watch. Everybody draw the line y equals 4. Actually, this one and the next one are tricky. But agree that's my axis of revolution right there, the line y equals 4? Okay, what comes next? Your represented rectangle. Where does it always go? Inside the region perpendicular to your axis of revolution. So there it is. There's my rectangle drawn inside the region perpendicular to axis of revolution. Now remember, you're rotating this region in that rectangle around here, aren't you? Around way up here, around the line y equals 4. So what's going to happen is this is going to swing around like this, and this is totally against the axis of revolution, so there's going to be no hole, is there? So no hole. So little r is what? 0. And big R, this is where you're going to make a mistake right here. Big R, do you agree, goes from here to here? Do you agree? From here to here, yes or not? Okay, all right, so look at your figure, and you tell me, in general, what is the distance from here to here, in general? No, x squared is from here to here. That's not what I want. Big R goes from here to here now, doesn't it? So what is it? 4 minus x squared. Very good, Sam. The distance from here to here is this whole distance, which is 4, minus this little distance down here, which is what? X squared. Isn't the distance from here to here x squared? And isn't the distance from here to here 4? So the distance you want, which is from here to here, is the full distance, which is 4, minus the bottom distance, which is x squared. Do you agree that that's a general expression for my big R? You see that? Yes? Okay, and so now let's set it up. So again, it's going to be pi times the antiderivative of your big R squared minus your little r squared dx from what x to what x? What x to what x? Come on. 0 to 2. Okay, I'll go one more step to clean up this mess. By the way, here you're going to have to FOIL, aren't you? Because U substitution is not going to work. So FOIL there, and you get 16 minus 8x squared plus x to the 4th, don't you? And then from there you would need to integrate and then plug in the 2 and subtract what you get when you plug in the 0. Multiply by pi, and you got your volume. Okay? Any questions on that one? Okay, 2 more tricky ones, and we are done with the hardest lesson of the year. All right. Ready? Do you want to try this one? We have time. Why don't you try this one? See if you can set it up without my help, and then we'll talk in a couple minutes. Try it. Do it. can keep going. I'm going to get started. There's 7 right there. So that's my axis of revolution. Okay. All right, then I always draw my representative rectangle where again? Inside the region and perpendicular to your axis of revolution. So it looks something like that, wouldn't it? Yes? And then imagine rotating that rectangle around that green line. So what's going to happen is this end of the rectangle is going to swing around like this. Right? This end of the rectangle is going to swing around like that. And you're going to get a donut, aren't you? Yes? Okay, let's talk about the outside radius and the inside radius of that donut. That's the next step, right? Okay, what's little r? I think little r is easy to see here. That's little r. The distance from there to there will always be what? You can see it easily. It's always going to be what? 3. Everybody agree that little r is 3 there? From here to here? Yes? Okay, now what about the outside radius from here down to here? What is that distance? 7, because it's 7 from here to the x-axis, isn't it? Minus this missing distance down here, which is just the parabola values, yes? Everybody agree that that's big R? Is that what you guys got on your own or not? Yes? Good. Okay, well that's the hard part. The rest is pretty easy, right? And so from there you just say the volume is going to be pi times your antiderivative of your big R squared minus your little r squared dx from what x to what x? 0 to 2. Okay, let's go one more step here and then we'll stop on this one. Okay, here you're going to have to FOIL, aren't you? You get what? 49 minus 14x squared plus x to the 4th and then minus, what's that, 9? And so you might want to simplify that a little bit more. And then don't forget to what? Integrate? Yes? Good? Okay, one more. All right, try this one. Go. Everybody try E. Okay, ready? Okay, you should all know that x equals negative 2 is the vertical line, and I'm going to draw right here. Everybody agree that's the line x equals negative 2? Okay, and so what I'm going to do is I'm going to draw my representative rectangle inside the region and perpendicular to my axis of revolution like that. Thank you. And then I'm going to imagine rotating that rectangle around this green line. And so what's going to happen is this end of the rectangle is going to swing around like that, isn't it? This end of the rectangle is going to swing around like that, creating a donut. Agreed? Okay? Now, let's talk about the outside radius and the inside radius of that donut. The outside, or let's start with little r. Little r I think is easier to see here. Everybody agree that the distance from here to here is my little r? What is the distance from here to there? Always. Look at it. What is it? 2. Okay. Now your big R is a little bit tricky, but do you agree that big R goes from here all the way to that line in general? Doesn't it? That's your big R from here to here. Well, what's the distance from here to the y-axis? Well, if you take your equation, which is this, and solve for x, you get x equals what? Square root of y? Does everybody agree that square root of y is the distance from here to here? Yes? But I don't want just that distance. I want the distance from here all the way to here. So you'd have to take the square root of y and do what to it? Add 2. And no, I know what you're thinking. Just because this has a 2 and that has a 2 doesn't mean you can cancel them out. I know that's tempting to do, but you can't. They have to be part of the formula. Is that clear? Yes? You can't go shifting stuff because then you're going to get a different looking solid. Is that clear? Okay? So don't do anything like that. All right? So just go with what it is and set it up. All right, so what do you got? Pi times the antiderivative of this thing squared minus 2 squared dy from what y to what y? 0 to 4. All right, and here you're going to have to FOIL. By the way, what would that look like if you FOILed that?
4 plus 4 is y.
Yeah, 4 plus 4 square root of y plus what? Y, and then minus this 4. And so basically the 4's cancel, don't they, before you even integrate? Yes? And then from there, you're going to have to write that as what? Y to the 1/2, so you can use the power rule for integrals and just go from there and finish it. Okay? Yeah, don't forget to integrate, guys, on the homework or on the test. All right.